Assalamualaikum. Hi everyone. Today we are going to learn chapter 9, Simple Harmonic Motion. We have 3 subtopics. The first subtopic is Kinematics of Simple Harmonic Motion. The second subtopic is Graph of Simple Harmonic Motion. And the last subtopic is Period of Simple Harmonic Motion. For lecture mode, face-to-face SLT, non-face-to-face SLT, we have 1 hour. For tutorial mode, face-to-face SLT and non-face-to-face SLT, we have 8 hours. As you can see on the slide, we have a few learning outcomes for 9.1, Kinematics of Simple Harmonic Motion. At the end of this topic, you should be able to explain simple harmonic motion. For 9.2 learning outcomes, graph of simple harmonic motion. At the end of this topic, you should be able to discuss the following graph. The first one is displacements against time. The second one is velocity against time. The third one is acceleration against time. And the last one is energy against displacement. Further explanation for 9.3, period of simple harmonic motion, we'll discuss in tutorial class and practical class. This slide shows an overview of topic simple harmonic motion. We have 4 views to cover for this topic, which are SHM parameters, SHM equation, SHM graph, and the last one is SHM system. We will review one by one on this lecture. Introduction to oscillations. Oscillations, in other words, mean periodic motion. The periodic motion is the back and forth motion of an object about a fixed point called the equilibrium position. As you can see, ball A moves back and forth from position A to negative A, pass through a fixed point. That point, we call it as equilibrium position O. This animation is an example of simple harmonic motion. This one is oscillation of a block attached to a spring. Number 2, movement of child on a swing. 3, motion of a pendulum. This one is the motion of a pendulum back and forth. The fourth one, motion of the piston in a car engine. The last one is vibration of an atoms in a solid. Kinematics of simple harmonic motion. Simple harmonic motion is a periodic motion without loss of energy in which the acceleration of a body is directly proportional to its displacement from equilibrium position or fixed point, and it is directed towards the equilibrium position but in opposite direction of the displacement. Mathematically, we can write A is equal to negative omega squared x, where A is acceleration of the body, omega is an angular velocity or angular frequency, x is the displacement from the equilibrium position. The angular frequency omega is always constant. Thus, A is directly proportional to negative x. Negative sign in this equation indicates that the direction of the acceleration A is always opposite to the direction of the displacement x. The diagram below shows that a simple pendulum moves to the right. As the object moves to the right, acceleration A is directed to the left. Object moves to the right, acceleration A is directed to the left. It shows that acceleration A is directly proportional to negative x. These are examples of SHM system. The first system is mass spring that moving horizontally on frictionless surface. The second is also mass spring system but moving vertically. And the last one is simple pendulum. This is the terms of SHM. 1. Displacement symbol x is defined as distance from the equilibrium position. SI unit meter. 2. Amplitude symbol capital A is defined as a maximum magnitude of the displacement from equilibrium position. SI unit meter. Number 3, period symbol capital T is defined as time taken for one cycle. SI unit is second. The formula for period T is equal to 1 over F. F is frequency. The fourth one is frequency symbol F is defined as a number of cycles in 1 second. SI unit Hertz or Hz. 1 Hertz also is equal to 1 cycle per second and also is equal to 1 per second. Formula for frequency is equal to omega over 2 pi. Omega means angular frequency or angular velocity. The formula is equal to 2 pi f. What is equilibrium position? Equilibrium position is a point where the acceleration of the body undergoing oscillation is zero. At this point, the force exerted on the body is also zero. Restoring force. Force which acts to bring a body to its equilibrium position is called restoring force. This force which causes simple harmonic motion to occur, and this force always proportional to the displacement from equilibrium and also always directed towards equilibrium. Mathematically, we can write restoring force Fs is equal to negative Kx. The negative means the direction of restoring force is always in opposite direction to the displacement x. For further explanation of SHM, consider a mass spring system that moving horizontally on frictionless surface. When the block is displaced to one side of its equilibrium position and released, it moves back and forth repeatedly about a maximum value of displacement x. The maximum value of x is called amplitude A, and the value of A can be positive or can be negative. If the block moves to the right, the amplitude is positive, and if the block moves to the left, the amplitude is negative. From the diagram, the block is displaced at positive x and the block is released. The block will move from positive x to negative x direction. The spring will exert a force that tends to bring the block to its equilibrium position. From Hooke's law, Fs, restoring force, is equal to negative Kx. Fs is known as restoring force. By combining Hooke's law and Newton's law equation, hence negative Kx is equal to ma. Rewriting the equation in terms of acceleration, A is equal to negative Kx over m. K over m is constant value where K over m represent omega squared. Hence, this equation becomes A equal to negative omega squared x. Any system that satisfies this equation is said to exhibit or to perform like simple harmonic motion. From above equation, we find that A is directly proportional to negative x. The acceleration A is proportional to the displacement of the block and its direction is opposite the direction of the displacement. Kinematics of simple harmonic motion. This video shows a mass on vertical spring system. The ball oscillates or moves up and down. As time passes, the oscillating object traces out a sinusoidal curve on the moving paper. This situation represents kinematics of simple harmonic motion. Simple harmonic motion can also be visualized as the projection of uniform circular motion onto one axis. Objects thus SHM behave very similar to objects that move in circles. The radius of the circle is symbolic of the amplitude A. This diagram shows kinematics of motion for an object in simple harmonic motion can be found from a relationship between simple harmonic motion with projection of uniform circular motion and sinusoidal curve. Displacement x. From the projection of the circular motion, we relate the sinusoidal curve by considering a complete round trip in SHM. The complete round trip in SHM is measured from starting point and also end up at starting point. By considering the diagram, starting point is from equilibrium position O, move to positive maximum displacement, positive A, back to origin, in other words, equilibrium position O, then move to the negative maximum displacement, negative A, and end up to equilibrium position O to complete one cycle. From this projection, the amplitude A represents the radius of the circle. As you can see, the object moved from equilibrium position to displacement x. From the reference circle, there is a triangle. From trigonometry equation, hence the displacement x is equal to A sine theta, where theta is equal to omega t. Then, the equation of displacement as a function of time in SHM is x equal to A sine omega t, where x is the displacement from equilibrium position, A is amplitude, omega is angular frequency, t is time, and omega t represent phase. This phase measured unit radian. SI unit of displacement is meter. What is initial phase angle? Initial phase angle indicate the starting point in SHM at time t is equal to 0 second. For example, if initially we displace the block at small distance x node, then the block is released, the block will perform simple harmonic motion. But for this case, the oscillation doesn't start from the equilibrium position at the time t equal to 0 second. So, this initial displacement need to be considered in SHM equation. Thus, equation will become x equal to A sine omega t plus phi, where phi represent the symbol of initial phase angle. These are the list of equations for simple harmonic motion. Displacement x, velocity v, acceleration a, kinetic energy k, potential energy u, and total energy E. 9.2 Graph of simple harmonic motion. First, graph of displacement against time. Since x is equal to A sine omega t, at t equal to 0, x equal to 0 means there is no initial phase angle. So, the shape of the graph for displacement x is positive sine graph. From the graph, one complete cycle for x-axis represents the period t, while the maximum displacement of y-axis or peak of the graph represents the value of amplitude. Another example for graph displacement against time is at t equal to 0, x is not at equilibrium position but start at positive A direction. So, the new expression is x equal to A sine omega t plus pi over 2 or x equal to A cos omega t. Hence, the shape of the graph for x becomes a positive cosine graph. If x starts at negative A, the new expression becomes x is equal to A sine omega t plus 3 pi over 2 or x equal to A sine omega t minus pi over 2 also equivalent to x equal to negative a cos omega t. Hence, the shape of the graph for x becomes a negative cosine graph. If x equal to 0 at t equal to 0 but v is equal to negative v max, the new expression becomes x equal to a sine omega t plus minus pi or x equal to negative a sine omega t. Hence, the shape of the graph for the x becomes a negative sine graph. Next, graph of velocity against time. Since v is equal to a omega cos omega t, hence the shape of the graph is positive cosine graph. The peak value of y-axis represents the value of maximum velocity, which is equal to a omega. Then, graph of acceleration against time. Since a is equal to negative a omega squared sine omega t, hence the shape of the graph is negative sine graph. The peak value of the y-axis represents the value of maximum acceleration, which is equal to a omega squared. For graph acceleration against displacement x, since a is equal to negative omega squared x, as we know a and x is directly proportional but always in opposite direction. So, the shape of the graph is a straight line graph, or in other words, a linear graph. The gradient of this graph represents negative omega squared. From the graph also, it shows that when x is positive, a is negative or otherwise. This shows that a and x always act in opposite direction. This is a summary for graph of simple harmonic motion. As you see, when x is equal to 0 or in equilibrium position, v is maximum and a is equal to 0. When x is maximum, v is equal to 0 and a also maximum. From the graph, it shows that x and a always directly proportional but in opposite direction. Energy displacement graph. From the equation of kinetic, potential and total energies, as a term of displacement energy against displacement is shown in figure below. This is the graph of kinetic energy K. This is the graph of potential energy U, and this is the shape of the graph for total energy E. From the graph at amplitude U is maximum, K is 0, and E is equal to U. But when x is equal to 0, U become 0, K become maximum, and E is equal to K. The last subtopic, 9.3, period of simple harmonic motion. 1. Simple pendulum. Simple pendulum consists of a particle-like bob of mass m suspended by a light string of length L that fixed at the upper end. The period T of a simple pendulum is given by T is equal to 2 pi sec L over G, where L, length of the string, G, acceleration due to gravity. The condition for the simple pendulum executes simple harmonic motions are: the first one is the angle theta has to be small or less than 10 degree. The second one is the string has to be inelastic and light. The third one, only the gravitational force and tension in the string acting on the simple pendulum. Second, mass spring system. There are two types of mass spring system. First is vertical spring oscillation and second is horizontal spring oscillation. The period of this spring oscillation is given by T is equal to 2 pi sub m over k, where T, period of the spring oscillation, m, mass of the object, and k, spring constant or force constant. The condition for the spring mass system executes simple harmonic motion are: first, the elastic limit of the spring is not exceeded when the spring is being pulled. 2. The spring is light and obeys Hooke's law. 3. No air resistance and surface friction. Let's test your understanding. The answer is D. Next, the answer is A. Next, the answer is C. Last one, the answer is A. For mastering SHM, you can learn more through videos. Scan QR codes given and watch the videos. Thank you. Bye.